Okay, so in this video, I'm going to do examples of just like coming up with Maclaurin series. So we're going to find 3 different Maclaurin series. So I know that a lot of times like you're asked to memorize these, but you also need to know how to like derive series. So e to the x is a very common series. And in this video, I am going to show you how to derive this if you didn't know e to the x. If you are looking for a video where what do you do when you already know e to the x, I have other videos on that, but in this I'm just going to derive all of these from scratch. So let's jump into it. Okay, so the whole thing with coming up with like a Maclaurin series, deriving it on your own, is taking enough derivatives to notice like patterns. So the first thing that I'm going to do is I'm going to just start taking derivatives of this. So obviously I'm going to have to use the product rule. So this is going to give me, so I take the derivative of x, which is just 1. 1 times e to the x is e to the x. And then I take the derivative, I leave x alone, and I take the derivative of e to the x, which is just e to the x. Okay, so there's my first derivative. So now we're going to take the second derivative. And so this is the derivative of e to the x is e to the x. And then if I take the derivative of this, basically the pattern repeats itself. So now I'm left with e to the x plus x e to the x. And I notice that this becomes 2 e to the x plus x e to the x. Now, you might already notice a pattern with this. And so this a little bit comes down to like intuition, comfort. So I am going to make a prediction of what the next term is going to be. I think the next one's going to be 3 e to the x plus x e to the x. So let's see if I'm right. So let's see, this becomes 2 e to the x. And then if I take the derivative of this, this becomes e to the x plus x e to the x. So yes. So this pattern has now kind of emerged. So as far as like how many derivatives do you have to take? It's as many as you need to feel like you have established a pattern. If you are very nervous about establishing the pattern, you can always take more derivatives, but I feel that this is enough for me to make a confident guess as to what my nth derivative is. And it's helpful to know this. So now this will be n e to the x plus x e to the x. So I'm on the second derivative, this was a 2. I was on the third derivative, this was a 3. So if I'm on the nth derivative, this will be an n e to the x plus x e to the x. Okay, so understanding all of this is very important so that you can establish the next part of the pattern. So now this is a Maclaurin series, so I need to evaluate all of these at 0. So we're even going to start with this one here. So this one will be my f of x. So let's see, where do I want to do this? I'll do this right here. Okay, so f of 0, so if I plug in 0 into all of this, this becomes 0 times 1, so this is just 0. F prime of 0, so let's see, e to the 0 is 1, and then this will be 0. So this is just equal to 1. F double prime of 0, so let's see, f double prime, this is what I was left with, 2 times e to the 0, which is just 1, so 2 times 1 plus 0. Okay, so again, a pattern is emerging here. So I have f triple prime of 0 will just equal 3. So now I've kind of noticed what the pattern is here, and I feel pretty comfortable in saying that for the nth derivative at 0, this will equal n. Okay, so once you've established all of this information, now what we're going to do is we're going to make some space, and this information here is kind of what I need to move forward. So I'll make some space. Okay, so now we need to really just like fill in the pattern for a Maclaurin series. So let me just state that. So here's the general pattern that you just want to follow. So you need to have this memorized to effectively do this. And I think it's like one of those things, like if you just have the format in front of you, it just makes it so much easier in how to fill it in. So, you know, feel free to write this down. I won't write this down every single time, but I'll at least like state, I think this is something nice to have next to you if you're a visual person. Okay, so I already calculated all of these f of 0 values. So now it's just filling it in. So this is 0, 1x, 2 over 2 factorial x squared. I actually would like to take this out to 3 over 3 factorial x cubed, and then let's see, this will be n over n factorial x to the n. Okay, so you plug all of this stuff in, and then once again, you're just like analyzing what happened with this. Can you like characterize the type of, I guess, cancellations or simplifications that you can make to this? So this will now turn into x plus, so 2 over 2 factorial means that this just becomes 1 factorial, which is just 1. So this is x plus x squared. 3 over 3 factorial will give me x cubed over 2 factorial. So I can see this pattern that's emerging now. So I have x to the n over n minus 1 factorial, right? Because n over n factorial, the n's cancel out, so I'm just left with n plus 1. Okay, and so now we are like just at the cusp of where we need to be to finish this. So I'll clear a little space. So after you've kind of analyzed all these patterns, then ideally what you would do is you would write this in series form. And so your series will start at 0, goes to infinity. This is going to be x to the n over n minus 1 factorial. And so that's it. That is the series. So that's why having this nth term is helpful, because that will probably help you just to create what the ultimate series is. Okay, so let's look at something a little weirder. So we've got sinh here. So I think the key for this one is to actually remember what sinh is, which is e to the x, e to the x minus e to the negative x over 2. So this will be the better way to think about this problem. So let's start taking derivatives. So what I actually want to do here is, if you're struggling with this, you know me, I'm always saying math is not a spectator sport. So I would really like for you to see if you can take the nth, like go take a couple of derivatives, establish the pattern, and plug in all your zeros. So see if you could find that formula for the nth derivative at 0. The worst that happens is you get it wrong, but you'll get more out of this video if you try. So hit pause here, hit play when you're ready. Okay, so if I take the derivative here, take the derivative of e to the x, that's just e to the x, and then when I take the derivative of e to the negative x, so I have to take the chain rule. So the outside will just be e to the negative x, and then the inside function is negative x, so the derivative of negative x is -1, so that will flip the sign here. So this becomes e to the x plus e to the negative x over 2. And I think in this case the pattern emerges pretty quickly, because when I take the second derivative, now when I take the derivative of this negative sign, or this positive sign, will flip to negative. So this is just going to go back and forth. So, okay. So how could I categorize this then? This will be e to the x plus -1. So really this is the only thing that's changing. So this is negative, and then for the first derivative it's positive, and then for the next derivative it's negative. So if this is negative, if I take this derivative plus 1, that'll give me an odd exponent, so that'll give me a negative number here. So this will be n plus 1 e to the negative x over 2. Okay, cool. So now let's go ahead and plug in all of our zeros. So this first function is my f of x. So if I plug 0 into this, this is 1 minus, really e to the 0 is still 1, so 1 minus 1 over 2, so this is 0. F prime of 0, so if I plug in 1 into this, or sorry, 0 into this, this becomes 1 plus 1 over 2, so that's 2 over 2, so this equals 1. And then if I go back to f double prime, so now I've got, this is e to the 0 minus e to the 0, so this will be 0 again. Okay, So I feel like we're already seeing a pattern established. It's just going to be a bunch of zeros and ones. So for the nth derivative then, so when is this going to be 0 or 1? So I notice for all of the even derivatives, this always equals 0. So what I notice then is that if this is the 2nth plus 1 derivative, so I call it the 2nth plus 1 derivative because that will give me an odd derivative, as I notice that all the odd derivatives are going to be destined to be 1. So 2n plus 1 designates an odd number. So this derivative will always equal 1. Okay. So now I think we've got enough to move this forward. So let me make some space. Okay, so I've summarized all my information. So let's use the formula. Okay, so in this case, this is my formula right for the series. If I start plugging stuff in, I get 0 plus x plus 0, and I can just continue the pattern for a second. So this will become plus x cubed over 3 factorial. So every other term I know is a 0. So it doesn't make sense in this context to use n. So this can always be manipulated to what you need it to be, because if I simplify this series that I see here, this really turns into x cubed over 3 factorial, x to the 5th over 5 factorial. So I want to write a series that will drop out all of these zeros. So what I'm going to do then is, instead of writing n, I'm going to write this as 2n plus 1 to the 0 over 2n plus 1 factorial x to the 2n plus 1. So that's what I want to do, and I know what this value is. So this value I can actually rewrite as just a 1, right? All of the odd derivatives equal 1. So now I can write the series. Let's see. I'll write the series over here just to the side, just to save space. Okay, so this is going to be x to the 2n plus 1 over 2n plus 1 factorial. So there you go. Okay, so this last one I chose because this is a little funky in that if you look at the previous two examples, so these two examples, the thing about them is that these derivatives just go on for forever, right? These just have continuous derivatives. You can take an infinite number of them and you will always have a derivative. What's interesting about this third one is that this one actually will at some point turn into 0, right? So what do we do with that? Well, when that happens, then that actually determines how many possible terms we're going to have in our series. In fact, the result is even a little silly. So, okay, let's go through the process. So actually, I want to ask you again to go through the process here. So go ahead, take your derivatives, evaluate them all at 0. Try to set up the Maclaurin series as best you think. If you get stuck, just hit play. Okay, so hopefully you did all of that. Remember, math is not a spectator sport. Okay, so my first derivative will be 4x cubed minus 3x squared minus 2. My second derivative will be 12x squared minus 6x. My third derivative will be 24x minus 6. Let's see, my fourth derivative will be 24. And then I notice my fifth derivative becomes 0. Okay, so let's go ahead and evaluate each one of these at 0. So if f of 0 is 3, f prime of 0 is negative 2, f double prime of 0 is 0, f triple prime of 0 is negative 6, and let's see if I can fit this in. The fourth derivative at 0 is 24. Okay, so we've got enough to make this series, so I'll clear some space. Got all that info tightly packed, but that will be good. Okay, so let's go ahead and I'll write out the form again that we want to use. Okay, so for this series, I did something a little different. So notice I actually wrote out just from f of 0 to the fourth derivative, because everything after the fifth derivative equals 0. So this is all that I've got, so I'm just going to write all this out. Okay, so let's fill in what we've got. So we said f of 0 is 3. F prime of 0 is negative 2 times x. F double prime is going to be 0 over 2 factorial x squared. F triple prime is negative 6 over 3 factorial. And then, let's see, what was the last one? 24 over 4 factorial. Okay, so let's sort all of this out now. So this becomes 3 minus 2x plus 0. So 3 factorial is 6. Oops, and I forgot the x cubed here, my bad. Okay, so 3 factorial is 6, so negative 6 over 6 will just give me negative x cubed. And then 4 factorial actually equals 24. So this is going to give me just x to the fourth. And so what do you notice? This is literally what we started with. So in this case, right, there's not like a good series that approximates this. The best thing that approximates this is literally the polynomial itself. So, you know, this is kind of the interesting thing with the Maclaurin series, is that, you know, it did actually cycle us around, but it gives us, you know, these infinite series that if you could go out an infinite amount of terms would perfectly approximate these. So I guess what I'm saying is that the Maclaurin series works. All right, so that's it for this video. If you found that helpful, I would love it if you'd hit the like button or comment or subscribe, and I will talk to you guys in another video. Thanks for watching.